So up till now, we studied class A power amplifier. In this lecture, we will study class B power amplifier. So first we will see the circuit of the class B, which is similar to class A with L and C included. So this is a circuit for class B, and here the operation in class B mode will be decided by this gate to source voltage, which will be 0. So here we will be making one assumption that the threshold voltage of the MOS is 0. If it is not 0, then this gate to source voltage has to be equal to threshold voltage. And we will continue to take the input sinusoidal waveform. So in this case now we will try to see the waveform for the drain current and this output current and the drain voltage. So that will then allow us to find out the efficiency. So which is the objective of main objective of this analysis. So first we will draw the waveforms. So here we first draw the input waveform. So we have taken gate to source voltage 0. So that is why my input is going to oscillate about this 0 line. Like this. So it starts from -pi/2 and it is positive till pi/2 and then negative till 3pi/2, and this is the amplitude of the input. So in this case, MOS is going to be on for the first half, which is from -pi/2 to pi/2, and it is going to be off. So when we say on, we don't actually mean as a switch. It is not completely short circuited. So it would be better to write maybe conducts and then off. So here off indeed implies that it will be open switch. There will be no drain current during this portion. So if you draw the drain current waveform, we will have this scenario. So this is the total drain current. So we will get non-zero only over the first half, and then we are going to get 0 for the second half. Here. And here we will be calling this IH to designate that this is the maximum value of half rectified drain current. Okay. So we see that our drain current is half rectified. So if we write the Fourier component of this is what we will get. So it will have a DC component equal to IH by pi, and then it will have fundamental component equal to half of the IH, and then it will have all the remaining higher order even harmonics. Here. So what we see is that it has a DC, and then it has fundamental, and it has second, then fourth, then all the even harmonics present here. So now we have to find out how much DC current is being drawn and how much RF current is getting delivered to the load. So here we see that we have this ID which has various harmonics including the fundamental. So you'll have to see that what happens to each of the current components. So for this case, we can see that how the DC flows and how the fundamental flows and how the other higher harmonics they flow through various parts of this circuit. So for DC, we see that DC will flow in this way. So for DC, the equivalent circuit is going to be this one. And because of the blocking capacitor, the load network will be cut off. So IDC is going to flow like this. For fundamental, I1. So the RFC will present an open circuit. And the blocking capacitor will act like a short circuit. And what happens to this parallel LC network is that it is going to be open. Why? Because if you find out the admittance of this LC, this will be susceptance of C plus C naught plus susceptance of L naught, and this is going to be 0 at the frequency of operation. So that means at frequency is equal to 1 by square root L naught C naught, the admittance offered YLC is going to be 0. That means the impedance offered is going to be infinity at omega naught. So that is why this LC path is going to be open circuit for the fundamental, which is this I1. So, and then what happens to the other harmonics, higher order harmonics? So for here we will be calling these as I even harmonics. So they will be flowing through this LC network. In fact, the C part of the for the even harmonics. So RFC will again be open circuited, even for even harmonics also, and blocking capacitor will be short circuited. So what happens is that this C for even harmonics will offer much less impedance. So all the even harmonics, they are going to flow through this path. So this So since this is a short circuit, that implies that any even harmonics will not be able to generate any voltage. So voltage generated by even harmonics is going to be 0. Here. So the drain voltage that we will see here is going to be sum of the drain voltages contributed for all these three cases. So for DC, the drain voltage that we will see here is going to be VDD, same as the supply VDD. For fundamental, the drain voltage that we will see here, VD1, that is going to be minus RL I1. And drain voltage for even harmonics is going to be 0. So the total drain voltage is simply going to be VDD plus VD1, which is going to be VDD minus RL I1. So the and what is this I1? I1 is fundamental of the total drain current for this half wave rectified. So the I1, that means the fundamental of this waveform is going to flow through the load, giving rise to pure sinusoid output voltage. And the other harmonics, they will flow through the LC network and they will get short circuited out. They will not contribute any voltage. So we can now draw the waveform. So this is I1. This will then flow through the load. To give rise this voltage. This will then get added with VDD. So this is the net drain voltage that we will see. And this is the amplitude. Okay, so from here, now we can find out what will be the efficiency for this case. So this is going to be the P load and PDC. So here PDC is VDD multiplied by DC current, and this DC current is amplitude of the half wave divided by pi, and P load is IP1 square divided by 2 RL. So IP1 is the fundamental of the drain current, which is this component. So therefore, the drain efficiency is going to be IH square RL divided by 8 VDD IH. So this becomes IH. There will be pi term here. So pi by 8 IHRL divided by VDD. And this can be written as pi by 4 IH by 2 RL VDD. So here we see that this one is IP1. So this IH by 2 into RL, this can be substituted as VP, because we know that the peak voltage that we see in the voltage waveform here, whether in the output or in the total, is actually consequence of this current flowing through RL. So this magnitude of VP is equal to RL into IP1. So using this, so we can write this drain efficiency 4 by pi into VP into VDD. So in general, this is going to be the drain efficiency for class B. But here, what we have taken is a scenario where the output swing, this VP is less than VDD. So to increase the efficiency, what one can do is increase the input. That means this A. So that will cause the increase in IH. That will also cause the increase in IP1. So that will lead to increment in VP. So the maximum swing that we can get is equal to VDD. So then we increase the VP by increasing the input. So we get the maximum drain efficiency is equal to pi by 4, which is 78.5% approximately. So here we see that efficiency is more, and compared with class A, which was 50%. So region is MOS is off for T by 2 duration. So by keeping MOS off for 1/2 of the cycle, we have been able to reduce the power dissipation. And that has led to the increment in the efficiency. So for this case, now we'd like to know that what is the power consumed by MOS. So instantaneous power we know is, so actually we want to know the average power consumed. This is VD into total drain current. So the average power PMOS is 1 by 2 pi, which is the one cycle of the MOS, starting from minus pi by 2 to 3 pi by 2. That means over one cycle, we integrate this quantity, the instantaneous power. But this waveform, the drain voltage or the drain current waveform exists only for the first half of the cycle. So integration limit gets reduced from minus pi by 2 to pi by 2. And the drain voltage we have calculated is VDD minus VP cos theta, and the drain current is IH cos theta. So this integration, if you carry out, it will give rise to where IH can be replaced in terms of VP, so that we have this as function of VP. So IH will be 2 VP by RL. So we have taken help that VP is IP1 RL, and IP1, the fundamental is half of the amplitude of the half wave. So using this, we have arrived at this equation. So here we see that this is a function of VP. The power consumed by MOS depends upon the amplitude of the output voltage. So now one would like to know that what is the maximum power that is consumed by the MOS. So for that, we find out the maximum value of this equation. With respect to VP. And this quantity, note down, is equal to 2 by pi, which is less than 1. So this is less than VDD. And we saw that when VP is equal to VDD, that time we get the maximum efficiency. But the maximum power dissipation in the MOS occurs for VP less than VDD. And, that is obvious also, because at the maximum efficiency, the power consumption should be low, not the maximum. Now, if we see the maximum power dissipation, it will turn out to be 2 by pi square VDD square by RL. So we saw that both the efficiency and the power consumed, they depend upon this output voltage swing. So we can just plot this wave relation and see that when do we get the maximum power consumed and when we get the maximum efficiency. So average power in the MOS is function of Vp, and if one plots it, this is the kind of plot we will get. So this is maximum power dissipation case, and this occurs for value equal to which we have calculated here, 2 VDD by pi. So when Vp is equal to this value, maximum dissipation occurs. And for this case, if we calculate out the efficiency here, so this will be pi by 4, 2 by pi, VDD by VDD equal to 1 by 2. So the output swing for which we get the maximum power consumption in the MOS corresponds to 50% efficiency. So at the peak of this curve, eta D is 50%. And we saw that when Vp is equal to VDD, that corresponds to maximum efficiency, and that was 78.5% approximately. And for this case, the power dissipation is, of course, it should be lower than what we have already seen for the maximum case. Now, if you see what is the maximum voltage and current that the transistor has to sustain, that means the stress on the MOS. So for finding out the voltage stress, we will have to look at the drain waveform, this waveform. So here we see that when we operate this circuit at the maximum efficiency case, in that case, the swing is going to be maximum equal to VDD, like this. So the maximum swing of the voltage that it has to sustain is equal to 2 VDD. So this is 2 VDD. Now the current stress. So this is going to be the maximum of drain current. So that is going to be maximum of IH, and this will be equal to maximum voltage swing divided by the load. So this is going to be 2 VDD by RL. So we saw that our load gets the pure sinusoid voltage waveform because this current is sinusoidal current is flowing through the load, and the higher harmonics of this waveform, they are getting short circuited by the C part of the LC tank, parallel LC circuit. But now suppose we do not have this parallel LC circuit, then what is going to be the various waveforms? V and I waves. So we have now this circuit. Here. So here we have total drain current and we will have total drain voltage. DC will continue to flow through this. So this total drain current, so now you can see that entire harmonics. So let us say IAC will flow through this, IDC will flow through RFC. So the total drain current now has only two components, DC and AC part. And this AC part, of course, will have the higher harmonics equal to the fundamental and I2, I4, so on, so forth. So what we saw was that the total drain current has this half-wave rectified form, this one, and the DC part is going to be the average equal to IH by pi. So this total drain current here, this now will have a DC part which is equal to IH by pi, and AC part which will be uh, this waveform shifted down. So 0 is now here. So it is now this waveform which is going to flow through the load, giving rise to the output voltage. And it will shift down by IH by pi amount. So this is now going to flow through the load. So we will have output voltage minus RL IAC. Here. And this output waveform will then get added with the DC, which is equal to VDD. That will give rise to finally the drain voltage. So our drain voltage now will look like this. So this is the total drain voltage. So we can see that the important role that LC is playing in ensuring that output waveform is sinusoidal. Okay. So here, what we found is that the MOS conducts only during the one half of the cycle, and it is off during the next half of the cycle. So we can put another MOS in such a way that the second MOS also conducts during the second half, but it is off during the first half. And then the both are contributing to the load. And in that case, we can still get the sinusoidal output. So that version is called push-pull version. So up till now, our circuit was essentially like this. Of course, RFC was also there. But now what we do is we use PMOS. And then we connect it to minus VDD. So this is one change. Second is the gate of both are simultaneously connected to the input. And then of course here you can note down that there is a no RFC and actually no CB is also needed here. So these are the two additional modifications in this push-pull version of the circuit. And of course, here also there is a no DC bias, and we assume that VTH is equal to 0 for this circuit, for these two MOS as well. So what happens here is that there will be zero DC at the common source, and then there will be time varying source voltage. And in this case, so our input is as usual, sinusoidal. So what we find is that for this portion, for the first half, the net gate to source for MOS 1 is going to be greater than 0. So which is from minus pi by 2 to pi by 2. So there is no DC, so this is simply going to be equal to input. So this is going to be 0. So this implies MOS 1 conducts. Now during the same first half, we see that the gate of the second MOS is connected to positive voltage because input is positive at this moment and source is 0. So for MOS 2, scenario is that gate to source 2 is equal to Vi, which is greater than 0, that means it is going to be off. So therefore the equivalent circuit is like this. So second MOS is going to be off. Yeah. So what will happen in this case? There will be a drain current which will be taking this path ID1, and ID1 will be, so this is our Vi, or the total gate to source voltage. So ID1 is going to be like this. And there is of course no ID2. ID2 is equal to 0. So for the first half, ID1 is half wave. So this is going to be 0 during the first half. Right. Now during the second half, so during second half, input is negative, less than 0. So during second half, what happens is this is negative, and source and this is going to be less than 0. This implies that M1 is off, but for MOS 2, VGS2, which is also equal to Vi, Vi is negative, implies that VGS2 is negative. That implies that M2 conducts. So now scenario is going to be different. This MOS is going to be off. However, this one will conduct. So for this case, equivalent circuit is going to be, first MOS is open, second MOS conducts. Actually, what I showed here for the ID1 is not the correct path. ID1 is not going to flow through RL, rather ID1 is going to be like this. The fundamental is going to flow through load, and the higher they are going to flow through this network, all the events. And for DC, there is a path through least resistance path through inductor. So the DC component of ID is going to flow like this. So here the drain current of MOS1 has a DC part, it has fundamental, and then it has all the even harmonics we have already seen, second, fourth, so on so forth. So now for the second half, the second MOS also contributes half wave, and for that we saw that total drain current D2 is going to flow through this MOS, which will have a DC part. So DC is going to flow like this. So this is IDC, and the fundamental is going to flow like this. And all the higher harmonics, they will even harmonics, they will be following this path. So there are two ways of looking at the functionality of this push-pull. Currently, we are interpreting in terms of the various frequency components of these two individual currents. So now what we see is, if you see the complete circuit here, then here we have ID1, here we have ID2, and then here we have the fundamental flowing through this loop. So this I1 plus ID1 is equal to ID2. That means the fundamental that the load will actually experience is going to be ID2 minus ID1, and they are going to be opposite of each other. So the net fundamental that will flow through the load is going to be twice of the fundamental that we had found here, which was 1 by 2 cos omega t. Anyway, this ID2 is 180 degree shifted version of ID1. So ID2 is ID1 omega t minus pi. So when we substitute this in ID1, we see that only the fundamental is going to get affected. The DC part and even harmonics, they are going to be as it is. So what we will see here is IH by 2 cos omega t into 2. Like one minus sign will be there. So we see that in this case, second interpretation is that the MOS one provides one half of the uh, sinusoidal function to the load network, and the second half is provided by the MOS 2. So on the whole, when you see I1, which we calculated, was actually ID ID2 minus ID1. So this is what we will be getting through the load. Therefore, the load voltage here is going to be RL into I1 is equal to minus IH RL cos omega t. And for this case, we can calculate the efficiency. So we have to find out the P load. So P load is I1 square RL by 2 and I1 we have found is IH and PDC is PDC for MOS 1 and PDC for MOS 2, and PDC for MOS 1 is equal to VDD and IDC provided by it. So this is equal to similarly PDC2 is also equal to VDD into DC current through it, and the DC current is IH by pi. Therefore, PDC is 2 VDD IH by pi. So therefore, the efficiency is 2 VDD IH pi, and this is IH square RL by 2. So this becomes pi by 4 IH RL by VDD. And IHRL is actually the amplitude of the output. So here we find that efficiency is going to be a function of Vp. So for Vp is equal to VDD, the efficiency is going to be maximum, and again it is going to be equal to pi by 4. Same as that of the previous case. Okay, so question will arise that what is the advantage we are getting here by going for push-pull configuration, given that efficiency is same. So here you can see that at any given input, the amplitude of the current that load will be getting is equal to IH, because this is going to be one half of the output current and this is going to be the other half. So here we see that the IH is the amplitude experience for any given input. But now for the same input, if you go to the previous class B, then we know that in the previous class B, the fundamental or the load current was the fundamental of this IH waveform, and this is equal to IH by 2. So for any given input, the first circuit will allow load to experience this much of current. However, the second push-pull configuration will allow load to experience IH amount of current. So for any given input, there is more current and hence the more power for load. So this is the main advantage of going for the push-pull configuration.